Morning, everybody. This is not jury duty today. Something worse is happening. An exam. So, what are your questions? And one, we'll get to you.
Now, we allow you to use that sheet that you gave us.
You know, yes. You don't have to tape it to your cheat sheet. Okay, you can just have it with you. Some of you are like, oh good, I got an extra, that big of a sheet to stick on, whatever, okay? So I can, tell you what, I will remember to print some out and I will have one with you at every table, right? So you don't have to bring your own, but that table of sign convention will be in the room. I might even just put it up here or something, right? But yes, I will make sure that you have all the sign conventions. That way you don't have to worry about bringing it, we don't have to worry about people using extra space on the cheat sheet. Seriously, you do worse if I give you 2 or 3 cheat sheets, it's pretty funny. I've done that test. Felicity.
Can you remind us what you want us to know about the people and the history of
People and history of light. Let's see here. So we started with Newton. Newton believed light was a particle. Along came, fill in the blank, Thomas Young, who showed that light was a wave. And what experiment did he do? The double slit. Didn't mention any experiments with Newton because he observed that light cast sharp shadows and thought it was a particle. He was wrong. But he didn't know about diffraction. So after Thomas Young and sort of the historical trend, there was experimental evidence for light being a particle. It was black and white photography. Okay. And then after black and white photography, pendulum swung back and James Clerk Maxwell produced evidence that light was a wave. How did James Clerk Maxwell prove that light was a wave? He provided the theoretical and mathematical basis in Maxwell's equations, and in solving Maxwell's equations discovered that there was a wave in the electric and magnetic field and it traveled at the speed of light. So there's the greatest hits, right? The things you need to know about the history of light, and I will pick one of those 4 things and ask you a multiple choice question, right? So it could be who initially thought light was a particle? The answer would be Newton, right? What did Thomas Young do, right? And the choices would be black and white photography, double slit, whatever, right? Okay, so a little bit. It's designed to be an easy question. Okay, it's designed to be a gimme. It's designed to be good, I did something right, and move on. So, worry about it, but don't worry too much about it. Did everybody see my announcement about number, whatever it was on the homework? 10, last question. It's being real stickler for sig fig. I think everybody has the same numbers on that question. Is that true? Did it randomize the nut values of the problem? But yeah, I think it's all the same. So the answer, so you'll calculate like 1.25 times 10 to the blah blah blah. Put in 1.3. For some reason, it will only accept 2 sig figs on that problem, even though sig figs are disabled on that problem. That happens every once in a while. Some code monkey got really excited and hard coded the sig fig thing. You ready?
Include this?
What?
Can we include this?
I'm going to provide it for you. This is the part where I start peppering you with questions? No? Okay.
When do we need to change wavelength from into meters in the equation? Like for thickness, we can leave it. But
Right. So the answer to that question is, unfortunately, it depends. But in general, so like the thin film interference problems, right? We're dividing by, usually we're solving for the thickness and dividing a wavelength by a unitless value, right? Like we're dividing by the index of refraction that has no units. And so physicists tend to get real sloppy, especially this physicist, but physicists in general will get sloppy when you're multiplying by unitless things and the thing's already in nanometers. Why convert it to meters only to convert back? Like there's no conversion that needs to happen. So the answer is it depends. You are always safe converting it into meters, right? If you're solving for, I can't remember what thin film problem I gave you, but if you're solving for a thickness and you give it to me in meters and my key's in nanometers, well guess what? I know how to read both. So it's not like I'm gonna knock you for that. But if you take a nanometer and divide it by a meter, I'm coming after you, right? Because that's mixing units. So the answer is, if you have multiple values that are all being expressed in different units, you got a velocity in a centimeter per second and a wavelength in meters, you've got to convert one of those into the other or it's going to just be messed up. Which is, again, why I always say just use standard units and you'll be safe. So, if you want to be fully safe, just convert everything into meters, seconds. So there you go. Did I answer your question? I think, yeah. It depends. Yeah.
What's the difference between mirrors and resolution?
So mirrors, right, is a convex or a concave situation, and find image distance, find object distance, find focal length, get your signs right on the thing. Resolution is yesterday's stuff, the Rayleigh criteria. Being able to tell the difference between objects at distance. So that resolution is the diffraction part, right? And people have been asking me more and more for this, so I guess maybe I should just start providing it. I guess it helps, I don't know. Corrective eyewear, chapter 26, right? No. I don't even know the numbers of this. Is this 26? History of light was 25. Lenses was 26. Mirrors was 25. Resolutions, are we in 20? We just finished 27, right? Telescope was 26, I think. Yeah, and thin films was 27. So we're like 26 heavy, right? 3 out of the 7 coming out of chapter. That seemed reasonable to me just because 26 was like a big thick chapter. Like it really was. It had a lot of stuff going on. Maybe it's because I don't remember numbers. I don't feel like it helps. But I mean, would it be helpful on the exam if the problem said, like right before the problem, chapter 26?
Like on the.
Chapter, yeah, like on the exam.
I feel like they do that before they start answering the question.
It'll be helpful. It'll be helpful.
I think it's just extra information.
I feel like it would have been more helpful in 2A.
Why are you asking us now, Mr. Mayo? You could have been doing this the whole time. From a teacher's point of view, there is a part of me that wants you to figure out the context of the question, right? That like you're reading the question, how do I know that this is thin films versus, right? Because the universe doesn't label it as, oh, this comes from thin films, right? And so there's that piece of it where we want you to start, big idea, what's the big idea about this question, and then narrow it down, right? That's a critical part of the problem solving process, but because the problem is that's not really practiced very much, because when you're doing a chapter's worth of homework, it comes from that chapter, right? Like, so in one sense, we're programming you to think about it on a chapter by chapter basis. And then comes along the exam and it's all mixed up and random and you don't know which one is which. And so it's wise to, yeah, that's,
I kind of like it because I know that it doesn't work.
I'll sleep on that one and think about it and probably tell you. The thing is that there's two different forms of the exam, right? So I gotta figure out a way to communicate that.
Can you go over the critical angle?
It's very critical. Critical angle. Let's do, oh, you know what, let's just do this. Here we go. Critical angle, so equation wise, the critical angle is the inverse sine of n low over n high. So I'm kind of reverse engineering my understanding of this, okay? That's what the equation says, but low and high, and what does that mean? Critical angle, the angle at which light will be reflected from a surface, like 100%. There's no transmission, there's no refraction, the light is going to stay in the material. That angle only occurs if light is trying to get out of a higher index and into a lower index of material. Okay? So at this angle, of course measured from the vertical, the light will be totally internally reflected. And I know that this comes about, this is actually like an extreme case of refraction, but we call it total internal reflection because the refraction is so big that it essentially doesn't happen. So the critical angle is the angle at which light will be trapped in a material. If the light hits the surface at this angle or bigger, it's going to bounce and stay 100% in the material. I know it has to be n low over n high because of how sine functions and cosine functions work. The ratio must always be less than 1. This is why the critical angle does not work if you try to go the other way. Because you'll get a ratio bigger than 1 and then your calculator will say that's impossible. And it is impossible, that just doesn't happen. So to calculate the critical angle, I know the ratio of my indices has to be a number less than 1, which means it has to be the low one divided by the high one. And then I take the inverse sine, I've got my angle and I'm done. Now, in general, the homework problems you did with critical angle, they were all harder, much harder than I expected them to be. Because you gotta find the critical angle, but then you usually have to do some like geometry along with it and right triangles, and I think one of the homework problems ended up having like trig identities in it or something. Gosh, it's terrible. Yeah, no, not a math class. Can you imagine me teaching math?
You cry just as much as us.
I toss out most of it.
Is the critical angle in that particular case the same as what the incident angle would have been?
Yeah, well, yes, the critical angle is the incident angle at which light is 100% reflected. Did I do critical angle on the exam? As a topic? Okay, just making sure. Didn't think I did. I don't remember. I did the exam before spring break, and as far as I'm concerned, nothing happened before spring break.
No, I'm guessing so. Maybe so.
Yeah.
Can you do number 8 on the chapter 27?
27. Inkjet printer. Oh. Dot separation immediately puts me into a mode of resolution. Right? How far apart two dots might be on the page. Normal viewing distances, the image has a normal look. The wavelengths, red, green, and blue are that. Diameter of the pupil is 2. For a viewing distance of 8 meters, what is the maximum allowable dot separate? Ooh, interesting. Okay. So they threw a lot of numbers at me, right? But dot separation, viewing distance, this is a resolution problem, right? So I'm gonna contextualize this in the Rayleigh criterion resolution setup. And for Rayleigh criterion resolution, it tells me that the minimum angular separation is 1.22 lambda over d. Did I get that right? I think I did. Okay. Theta minimum, that's an equal sign right there. Theta minimum can be rewritten as y over L, the separation distance divided by how far away that thing is. And so the picture I always have in my head is that two things are separated by distance y, and that those two things are distance L away from somebody or something that's doing the looking. Okay? So they gave me a viewing distance of 0.8 meters, 80 centimeters, right? Which is kind of far. Like 25 centimeters would be normal, right? Anyway, so viewing distance of 80 centimeters or 0.8 meters, okay? They want the biggest allowable dot separation so that we can basically not see the dots, right? That's what they're going after. So we are solving for y, right? What is the dot separation? Okay, so I'm going to let y over L be equal to 1.22 lambda over d. I'm going to solve for that y. It's going to be L times 1.22 times the wavelength all over d. The things that I have control over in this problem, the L is set. It's 0.8 meters. The diameter is set, 2 millimeters, so 2 times 10 to the minus 3. And then the wavelength changes. I've got a choice of wavelengths here, don't I? For these different colors of light. And they want the biggest. Why? The biggest separation that's allowable, right? So which of the wavelengths am I going to choose for this biggest separation? Whatever the biggest one is, red, right? 660 nanometers. Let me check, make sure that that makes sense. For viewing, this is what is the maximum allowable dot separation. The distance between dots is going to depend on the wavelength of light I'm using to look at it, right? And the shorter the wavelength of light, the closer the dots can be together. If I use red, oh, this is a little bit tricky. So, if I calculated this for the red, I would get a big Y, right? If I calculated for the blue, I would get a small y, wouldn't I? That's just putting in the numbers, right? But we want to be able to see all the colors as a smooth image. So the biggest allowable distance would be the shortest y. Because that means that blue, green, and so anything that's, right? Red says they can be this far apart, right? But blue says they can be this far apart. If we answer for the red wavelength, then blue is going to say, oh, well, now you can see the dots. So we actually want the shortest distance for the maximum resolution. All the other colors will then be above that, and we'll see a smooth image. So ooh, they tried to trick me there. But I used the gray matter. So we're going to use the 470 nanometers. That's the largest it can be, and all three of these things will be able to see that there's not dots. And then I put in numbers, whatever those numbers are. I'll let you guys have fun with those numbers. These numbers are evil. You know what's going to happen tomorrow is I'm probably going to decide to give you the chapter numbers and then screw up the chapter numbers. Very, very normal. Other questions? Yeah.
I think question 10 on chapter 26's homework is a corrective eyewear problem. Could you go over that?
I mean, chances are it is the right, it is the right chapter for that.
That's pre-spring, we knew how to do it.
Right,
Everything I've done.
right, and now it's like, what did I do? Trying to think. I don't think that I have ever said to myself, you know, past self, you took too many notes. Usually it's past self, why didn't you take enough notes? Right? Why didn't you leave a clue as to what you were thinking? But never had it be the opposite. What'd you say? Question
I
number
think it's 10.
10. Large print in a newspaper?
Yeah,
Yeah,
I think it's an eyesight question.
it is an eyesight
It
question.
says eyes a lot.
Woman could read only when it is at, okay. So, this woman has to hold, okay, well, first of all, we know she's old because she's reading a newspaper, right? Okay? Second, that was me. To newspapers. Is that a nearsighted or farsighted person? A nearsighted person has trouble seeing far away, right? And a farsighted person has trouble seeing up close. I don't make the rules, it's just the way that we taught it, okay? So, this woman is having trouble seeing up close. How do we know that? What's the normal up close distance? 25 centimeters, right? Okay, so if this woman's near point is not 25, then she's farsighted. For a nearsighted person, what's the problem? What's not at the right spot? The near point or the far point? It's the far point that's not at the right spot. Where's the normal far point for anybody? Infinity, right? And so anybody with a far point that is not infinity is what? Nearsighted. Meaning they can see up close, they just can't see far away. This is where the most confusion out of corrective optics comes from, right? Is this terminology. So make sure you got that terminology down, right? So a far-sighted person has a problem with their near point. It's not 25. And a nearsighted person has a problem with their far point. It's not infinity. Okay, so since this person's near point, the point at which they can comfortably see an object in front of their face, is not 25 centimeters, okay? This person is farsighted. So, a farsighted person's eye is corrected by what type of lens? Your choices are converging or diverging. Didn't sound very certain. This is 100% true. It never changes. A nearsighted person needs a converging lens, a magnifying lens. Okay? So what's the opposite then? If they are, I said that wrong, go ahead. Did I say nearsighted?
Yes.
Can we back up the YouTube and re-record that? A far-sighted person needs a magnifying glass, a converging lens. A nearsighted person needs a diverging lens. Take that to the bank. That's true, right? That never switches, okay? So, in answer to the question, what kind of lens is used in her glasses to correct the eyesight? That would be a converging lens. This person is farsighted, meaning they can see far away, they can't see up close, so they need a converging lens to magnify what they see. Okay. Part B. What should be the refractive power in diopters of her glasses or that far from her, I hate that. So when they can read the newspaper at a distance of 21 centimeters from the eyes. Okay, so we're now asking for focal length and the inverse of the focal length, refractive power, okay? So now we do a calculation and, I mean, it's the same, like, equation we've always been using, right? Since they're asking for refractive power, and the refractive power is the inverse of the focal length, we don't need to invert our final answer. What we do need to do is make sure that we get the signs right. So for all corrective optics, for anybody wearing glasses or contact lenses, the image distance is always what? Positive or negative? It was a good spring break, wasn't it? It's always negative. Why is it always negative? I don't care if I'm like drawing the eyeball over here and the lens right here. Where's the front side of the lens? Is it in their eye or is it the other side? It's the other side. The objects are all out here, right? Okay. Where are we putting the images for people to focus on? Not on their eye. This is where everybody goes wrong. You're thinking about like the light converging on the retina or something, okay? This lens right here, right there, okay, that lens is producing an image somewhere. And it's producing it in the front side of the lens. This lady's far point is in the wrong spot, okay? So, oops. I should probably draw that like this. Her far point is her near point.
It wasn't spring break, wasn't it?
No. This isn't spring break. This is my dyslexia. I'm trying to be really careful and it's screwing me up. I should just let it flow. Her near point is not where it should be, right? The normal near point is at 25 centimeters, but hers is at 56. She can't see anything at 25 centimeters. Glasses or not, she can't see anything at 25 centimeters. And if you can remember something, remember this. You are forming an image where the patient can see it. Where can this patient see something? At 56. So you are putting the image at their near point. That image is on the same side of the lens as the object. In corrective optics, the image and the object are on the same side of the lens. And since the object is always the front, that means the image is on the front. And what does the table tell us for image distance, which is on the front side of the lens? It's negative. So when we do this calculation, we're going to put 1 over 25. Hold on to that thought for a second. Plus 1 over negative 56. I actually have to go back and correct this because this problem is being annoying. The object distance is the distance of the object from the lens, right? And this problem gave me a little bit of a curveball, right? The distance she's holding the newspaper is 21 centimeters from her eye. But the lens is not on her eye. Where is the lens? It's 2.7 centimeters in front of it, right? So the object distance is going to be 21 minus 2.7. I'm not going to do that to you on the exam. You don't need to correct for the lens eye distance, right? Give you the distance from the lens. Optometrists need to worry about that stuff, not us. Okay, but the point there is that the object was located at whatever 18 point whatever from their eye, okay, and from the lens. Key points, image is being formed on the same side as the object, so it's going to have a negative image distance for a far-sighted person. Where are you putting the image? their near point. And for a nearsighted person, where are you putting the image? At their far point, which is not infinity for that point. What's the object distance for the nearsighted case? Far-sighted people are holding stuff at 25 centimeters in front of their face. Nearsighted people, what are they trying to see? Infinitely far away. So the object distance is infinity for nearsighted people. And then for farsighted, the object distance is 25 or 21 or whatever it is they tell you in the problem. Normally 25 if they don't tell you. I think all of that's confusing because farsighted and nearsighted feel like opposites of what's actually going on, right? And it feels like there's a few double negatives in all of those statements. Don't use no double negatives, right? It's like, what? Right? And our brain starts to like, wait, was that a minus and a minus makes a plus, right? So try to just make sure you're nailing the definitions of nearsighted and farsighted and what that implies about where people can see. And remember that we correct vision by making images where those people can see it. Whatever their values are, that's where we're putting those images. And if you're dyslexic, make sure you write it all down correctly. I did that once, I had it all opposite. And my teacher came to me, he's like, why did you do this all exactly wrong?
Are you giving us a sign sheet?
I'm trying to figure out how I'm gonna do that. I'll probably just write it up on the board, just to save trees.
Can you go over chapter 27, number 5? On that one?
You said 5, right?
Yeah.
Oh, always feels like coming home. All right. Films on glass plane, film thickness. What is the longest possible way they get back in light for this film has been designed? All right. So they did a picture for me. Look at that. Okay. What am I going to do first? What's the first thing I got to figure out? Like what the bounces do, right? But what flips, what doesn't. So it looks like it's in air, right? They don't tell me anything else. So I know that this is 1, this is 1.33, which is water. That's pretty funny. And then the glass plate is 1.52. Okay, so 1 to 1.33, what's that bounce do? 180 or 0? That's 180. And then 1.33 to 1.52? Also 180. So, if I leave things alone, what do I have? 180 and 180 are the same number, so it's constructive. If I change, the second one by an additional 180, then I would get destructive, wouldn't I? Okay, so I've derived the application and meaning of the physics of the situation. What is the longest, okay, so they're telling me the biggest possible wavelength of light for which this film has been designed. What has it been designed for? Non-reflective coating. The word non-reflective implies which of these two cases? Destructive, right? You want to kill the reflection. All right, so I'm gonna use my destructive case. Longest possible wavelengths, that's 2nt over m plus a half, equals my wavelength. So I've got 2, what index do I put in there? Since I've got 3 in my problem. The film's index. 3, thickness, 1.02 times 10 to the minus 7. All right, and then I've got m plus a half on the bottom. So they want the longest. So I've got control over m, and what could m be? Integer starting at 0 in this case, because it's 0 plus a half, right? Okay. So to make this wavelength long or big, right? The biggest this thing can be is when the smallest the denominator can be. Did I get that right? Okay. So what's the smallest this denominator could ever be? With m equals 0, right? So let m equal 0, and then calculate what that wavelength is. Now, looks like that wavelength might not be in the visible. It's twice something in the visible range. Let's see. So 1.33, 1.02 is 7. I already put the 2 in. I don't remember if I did I did the 2, but I didn't do the other 2. I got 5.43. Now I'm going to screw up again. 5.43 times 10 to the minus 7. So 8, 9, that's 543 nanometers. Did I do that right? 5.43, move that twice makes this 9. Okay. So yeah, 540, is that the answer? Assuming I use my calculator correctly. Yep. That's the longest one, right? If it had come out at this, for some reason it had come out as like 1200 nanometers or something like that, that's not visible. And I would tell you what the visible range is. It's always 400 to 700. That's what I remember. It's easier to remember. Some people argue it's 450 to 750 or whatever. It's 400 to 700.
So this might be a dumb question,
No.
but since there's two 180s, it equals a 360, which would be constructive. So why was it destructive?
So you're a little bit wrong, but I'm glad you asked the question. It's a comparison between the two rays. They're both 180. Right? And so that's constructive. But when we do the second, when we're over here in this one, that m plus a half says add 180 only to the second one. So then we would have 180 and 360,
Oh, okay.
and those are different. So they would cancel each other out. Did I help to
Yeah, it makes more sense.
clear up the confusion there?
So the image doesn't really matter as long as the question is giving you the detail of reflective or non-reflective?
Yeah, we're not forming images here.
Well, no, like putting the 180 on the roof.
I mean, 180 is just like a label. It's a phase shift.
So when the question says non-reflective, I could just use the equation with the plus.
No, it depends on the situation because I could have a situation of 1.331, 1.33. Okay, the light comes in. What's that phase shift?
0.
0. Okay, what's this phase shift? 180. Okay, now if I leave it alone, what is it? It's destructive, right? And if I shift the second one by a half, or 180 degrees, 360 and 0 are the same thing. So it's totally opposite, right? That's why you go through each time and make sure you know what the phase changes are.
So non-reflective coding indicates that that's destructive.
Destructive. So if I had this situation and I wanted a destructive coating, I would use that.
What other terms would be used if you want like deconstructive, like absent as
Absent, non-reflective, not there, don't see the color. Yeah, there's usually some negative adjective that's applied to bright, reflective, intense. They use the word magnified sometimes, which is a bad word to use in optics. Okay, I didn't get a chance to talk about this very much class, so I'm gonna talk about it right now. My graduate work, okay, was to build multi-layer thin films, so more than one layer, okay? Such that the light would bounce off this one, bounce off that one, bounce off that one, bounce off that one, and then we would add all of these up together at multiple angles, okay? And our whole goal was to be able to take pictures of particles that were trapped in the Earth's magnetic field that were emitting very specific wavelengths of light. What our multi-layer structure had to be, and this structure was put on top of a telescope mirror. So we were the reflective coating for the telescope, right? Other people made the shape and all that kind of stuff. We were just doing the reflective part. And our coating had to do two things. It had to destructively interfere two different wavelengths while at the same time constructively interfering a third. The only people in the world at the time that could do this were Intel and AMD and Motorola. Those are chip manufacturers, but the things they use to make chips, the photolithography they use, uses certain coatings in the X-ray region of the spectrum. And NASA came to them and said, we want to do this, and I think it was Intel said, okay, give us $10 million and we'll think about it. My graduate advisor was at the meeting conference and he stuck his hand up and said, hey, I have 10 graduate students. You pay for their college and we'll get it to you for $100,000. NASA's like, you're on, right? Okay. So he came back from that trip and we're all sitting there picking our nose thinking our life is good. And he's like, everybody get in here. We're like, what? He's like, I said that we could do this for $100,000. And we're like, are you crazy? Like, he outlined the problem and I'm like, nobody can do that. Like nobody even knows what the index of refraction is for having these materials at those wavelengths. He's like, yeah, I know. But they're gonna pay for your graduate school. All right, oh yeah, that's possible. We can do that. So I paid exactly that much for my graduate school. And we did it. We did it in 18 months. It was a 12-month deadline. We did it in 18 months, but that's okay. The part that MIT was building, it took them 3 years. So we beat them. But yeah, we did stuff that had never been done before, and that satellite orbited the Earth. It was the very first of the satellites that does space weather, taking pictures of the Earth's magnetic field, knowing what it's going to do, and all that kind of stuff. So, yeah, don't tell anybody don't let anybody tell you it's impossible. Even when 10 graduate students all look at the advisor and go, "That's impossible." He's like, "Yeah, I know, but we're going to do it anyway." The answer, I know this will mean nothing to you, turned out to be uranium oxide. We use intervening layers of uranium and silicon in our multi-layer thin film, and we couldn't figure out how to get the non-reflective for the third wavelength. Like we could get the maximum reflection, we could kill the other one in the same layer. Just like, oh, we're struggling with that third layer, because usually a layer doesn't do more than one thing. To make it do two, you have to be lucky, And to do 3 was why Intel was like, yeah, $10 million, right? But it turned out that, and this, most science happens by mistake. You go in with an intention to find something and then you realize you're asking the wrong question and you discover something else. And this is kind of what happened to us. We were getting desperate. We were trying to figure out, we were doing all kinds of different materials, and one day we were sitting there and we decided to go back and measure something that we had done 6 months earlier. We had kept all of our tests and we re-characterized it, we re-measured it, and magically it had fixed the problem. And we're like, but we didn't touch it. We measured it before and it wasn't doing that now. So we ran down to the chemistry department and we're like, we need whatever best microscope you have. And they're like, well, we don't use microscopes. We're like, ah. So it turns out the geologists had what we needed. They had a device that could see crystal layers in things. And so we're like, we need to know what's going on. And it turned out over a period of time, a thin layer of uranium oxide built up on the very top, and it was killing the one that we needed killed while letting all the rest through. And we're like, this is it. And then thereafter, when we started making these things, we would make them, and then we would pump oxygen into the container to get that top layer of uranium to oxidize, and we got to watch that take off on a rocket. Had to wait 40 days for it to degas and get used to the environment of space, and for 40 days, well, actually more like 140 days. I was super worried that they were going to turn it on and they were going to see like my thumbprint. We were so careful making that final mirror. Because I was the one making the stuff. I was the team lead on creating the coding. Others were measuring to see, like I would make it, they would measure it to see if I made what I said, what theorists told us to make it. I was convinced my thumbprint was going to be on there. But it wasn't. It worked. Yeah, that's why I like this stuff so much. I lived and breathed it. I have done nothing for a year and a half. Really did. I mean, I think I took classes in there somewhere. I mean, I know I did. I've got the transcript that said I did. I don't remember a thing from those classes. I was like, if it doesn't have anything to do with thin films, I don't care. Yeah.
How much does a project like that cost you?
So, well, we lowballed our number. The mission was I think the whole mission was $20 million. It's called the IMAGE satellite. Imager for like magnetopause and global exploration. NASA's so good at their acronyms. And it was a $20 million mission, which is really low for NASA. Like it was, they were trying this sort of new thing where they did faster, better, cheaper, and it didn't really work. But ours worked. $19 million of that was launch, like just paying for the rocket to get the thing off the ground, right? So that left basically $1 million for 6 instruments on the satellite. So building the satellite and putting 6 scientific instruments on it. I remember going to the launch, and we were all like graduate students in our second year, because we had done half of this research as undergraduates, and we finished it up as graduate students, and so we hadn't yet gotten our master's degrees. And we're sitting at the launch thing and we're meeting all the other people that we had only ever talked to on the phone, like video conferencing didn't exist and all that kind of stuff, right? So we're meeting all these other students that had worked on other parts of the satellite. And they're like, yeah, I did my PhD work, this is my PhD, and we're like, wait, you got a PhD for this? And they're like, yeah, isn't this your PhD? And I was like, dude, I haven't even got my master's yet. This is my master's thesis. They're like, whoa. I went over to my advisor and I was like, they're getting PhDs. What's going on? They're like, yeah, you started early. Yeah. Any other questions, or should I take more trips down memory lane? I say this without arrogance or pride. I'm a good experimentalist. Like, I know how to get things to work in like the physical world. Like, I can build something, I can fix the vacuum system, I can get the coding down, whatever. Even outside my field, like I just seem to have a talent with like getting computers to do my bidding and all that kind of stuff. So I'm a good experimentalist. I'm not sure I'm a good physicist. Like, I don't have a lot of patience for theory, but if you need, and so sometimes my advisors were like, why aren't you an engineering major, right? And the problem was I always wanted to know why. Engineers were always like about how, like get it built, and I could do all that, but I wanted to know why it was doing what it was doing. And so that's the part of physics that I've always really enjoyed. I did not enjoy sitting down with the code monkeys, the theorists who were typing computer code to try and predict what materials I was supposed to put on there. Especially since they kept predicting things like beryllium. I was like, I am not going to put beryllium on the surface of these mirrors because if I breathe any of that, my lungs dissolve. Like, it's just not going to happen. They're like, what about uranium? I'm like, yeah, fine. No problem. You breathe beryllium, you get something called beryliosis, which dissolves the alveoli in your lungs. I think the beryllium dust only has to be 1 part per billion concentration to start that process. Most coal miners, the black lung disease and all that kind of stuff, that wasn't caused by coal, it's caused by beryllium. Don't breathe coal, but beryllium's way worse. Yeah? Like, can I jump over them? So 3 kinds of mirrors that we talked about. The boring one, which is the flat plane mirror. And that's just angle in equals angle out. I'm not asking you about that, okay? And then there were concave and convex mirrors. Concave and convex refer to what? Like, how do I know when something's concave or convex? If I have a mirror like this and its focal point is right here, and its shiny side is on this side, what kind of mirror is this? That's a convex mirror. Okay? What kind of focal length does this have, positive or negative? Negative focal length. Okay? Because the front side of a mirror is always the side that's shiny, right? The side that the object's on. Okay? But what if the shiny side is over here? Now what kind of mirror is this? It's concave, right? And it wouldn't make any sense to put an object over here if that's like the not shiny side of a mirror, right? So the object is always on the front side or the shiny side of a mirror, and then if the focal length is on the same side as the object, you've got positive focal length's on the opposite side. For some reason I'm drawing these in reverse, I don't know why, but I am. Right? Then now I'm going to have a negative focal length. So this is a positive focal length. This is a negative focal length. The front side of both of these mirrors is on the right. I think a lot of pictures I drew in class, everything was on the left, wasn't it? This would be front, positive focal length, negative focal length. It's not the whether it's on the right or the left, right? Front side of a mirror is always the side the object's on, it's always the side that's shiny side's on. After that, once you get your sign conventions down, it's a matter of the lenses. It's the same equation for mirrors and lenses, right? I wonder sometimes it would be a little bit easier if that equation were slightly different, right? But it's the same equation, which can kind of throw people for a loop. Wait. The same relationship for both mirrors and lenses? Yes. What changes are the conventions, right? What changes is whether we use positive or negative signs. Boy, my allergies are starting to go off. Did I answer your question, Jordan? Finally got out of being sick and having to wear a mask. I might have to put a mask back on just for my allergies. You guys will see me wear a mask starting at the end of April, like the last week and a half of April. My wife and I are going to England right after finals. And we do not want to be sick. Like, can't be sick. The British will shoot us or something. We're celebrating our 25th wedding anniversary on year 28. Because we were supposed to go in 2020. So, oops.
Have you guys been there before?
I've been to Iceland. That's the closest to the prime meridian I've ever been. Well, yeah, it goes all the way around here. So, and then I've flown over the international date line on the opposite side of the planet, so now I get to go to
Did you go in the winter?
to Iceland? No, summer.
You didn't do the ice skates?
No. Well, no, we walked through a lot of, yeah, but it was warm. Well, for Iceland.
I thought I was gonna die.
Yeah? Yeah, yeah.
I didn't think I was gonna make it.
Yeah, no. But Iceland has really good hot dogs.
Thank you.
It's got really good fish.
Very long.
Yep. Guys are not asking me questions, so I'm starting to.
Well, diffraction gratings being test?
No. I put resolution down, that's your only diffraction.
For telescopes, there's only the two equations there.
For telescopes, this is dangerous. The magnification of a telescope is the focal length of the objective of the focal length of the eyepiece. Is that right? Well, okay, negative sign. Yes, that is correct because telescopes make big things, make faraway things bigger and closer. So, and the objective is always the big thing and the eyepiece is always a small focal length, and so that's how you get the biggest number. And then the length of a telescope, this one's always easy to remember, is the sum of the focal lengths. So if by those two equations that's what you mean, then yes. The minus sign on the magnification equation for a telescope is debatable. I mean, yes, a refractor, a two-lens refractor will always invert the image, but astronomers think upside down anyway, so it doesn't matter. Were you aware that the moon is upside down in the southern hemisphere? I can tell by your confused looks. You weren't aware. All the flat earthers might want to leave. So let's say, okay, so here's Earth, and I'm just going to put an arrow to represent the moon, okay? So like, I could draw the moon, but like, the north pole of the moon's here, south pole of the moon's here, right? In the northern hemisphere, we're standing in the northern hemisphere, we would see north be north and south be south. What does the person standing down here see? It's upside down. So when you cross the equator, your view, what you see the moon doing, here's the moon, okay, and all the craters and whatever's on the moon, okay? When you go to the southern hemisphere, that's what it looks like. Astronomers do everything backwards. Because they don't have a choice. The eclipse on Monday, we will have, I think, it's like 50% coverage of the sun, which means that we might be able to tell that the sun's a little bit darker, but not that much. Trying to decide if I'm gonna pull the telescope out and put the sun shield on it. It's not really working. What? Yeah, you can hold it. Don't hold your cell phone up to it. You can hurt the sensor on your cell phone. 50% is kind of not working. 90%? I'd cancel class. I was gonna go. My sister's house is in the path of totality, but I get in trouble with the state of California if I miss too many classes. And it was starting to threaten your guys's, this class counted towards your majors. So I was like, yeah, it's not good. And it's not, I mean, Eclipse is not really on my bucket list. Would it be cool to see? Sure, but there's other things I'd rather do. And I'm trying to do my best impression of an attention deficit mind, just to keep the conversation flowing. But my family's convinced that I have caught attention deficit disorder, having been surrounded by 3 of them for the last 30 years. So they claim I'm getting more and more attention deficit. When my wife and my kids are talking to each other, I cannot keep track. I simply cannot keep track of how the conversation is flowing. What was the connection between those 2 topics? Oh, no other questions? You don't have to stay. I will see you, let's see, Thursday? So tomorrow I am lecturing in my Physics 2A lab. And I'll probably only do that for like an hour and 10 minutes. So there's a possibility if you stop by the lab, I will be able to answer questions if you got them. Right? Well, it's to say it's 8 to 10:50 and 11 to 1:50. Sort of the standard lab time. So if you are desperate, you can pop in. If I'm talking, you just have to wait. But chances are I'll be free to help you. But I'll definitely stay for the next 10, 15 minutes still.
Was there class?
Yeah. I think it's only Clovis Unified that had the day off. Fresno State also had the day off. So the recording's up on.
Also, how far would you have to go from the
Equator? I think it's like 100 kilometers either direction. The moon is like more or less directly above on the equator. It's kind of like, there's no up or down. So yeah, you gotta get offset just a little bit.
Question. So for the distance of the object, if it's positive, does that mean that the image distance is also going to be positive?
Totally depends on where the image is forming.
It depends for both mirrors and lenses?
Yeah. Yeah.
Thank you.
I was asking, but are we still allowed the cheat sheet?
Yes.
Okay.
But I'm gonna give you the measure.
Thank you.
I did a good job. I got my application got accepted. Sorry,
Application got accepted. Okay.
application got accepted.
Yeah.
But I'm like number 53 of a couple hundred. So
Nice.
probably they're like applying for license all the way down to Sanger.
Yeah.
So I'll get one in Fresno probably.
Nice. Nice.
But so that I wanted to ask the 2 jobs.
Yes.
Are they, if I were to apply now for them, would it be for next semester?
I think you can say what you want it to be for. They'll probably say, go now. is usually what they say.
I could come now, I guess.
Yeah.
It'll
But go
take a
apply.
couple months
Yeah.
for the libraries.
Yeah, yeah, no, go apply and see if they, you like, Mr. Bayless sent me over and said, I should apply. They might go, oh, yes. Cause I know we have very few physics 2 tutors. Mostly it's physics 4 tutors.
Like 2 or 3 people.
Yeah, it's the physics 4 tutors are trying to tutor the physics 2 students, so they're usually doing too many hard things. So, whipping out those tutorials.
I don't know, I'm nervous.
You'd be great.
If I were to have 2 jobs instantly.
Right, 0 to 2. When it rains, it pours, right?
Big bucks though. We can borrow.
Alright, bye.
Yeah.
See you.
So you may already have an answer for this, but do you know like which homework problems would be the best ones to have fully down?
None of them, I mean, I think having the homework problems on the cheat sheet doesn't help.
Yeah,
But
like
having
there's been a
to-
couple cases of like looking for very particular ones,
yeah.
like I need to know how to do this kind of thing.
Right, you follow the topics list and try to line up the topics, that goes on the question.
Good.
I'm gonna help her with a cheat sheet.
Oh, okay. And then the other thing was just a comment about the whole attention deficit thing is, I weirdly have noticed people with attention deficit seem to hang out with other people that have attention
Because
deficit.
they can follow each other. They notice the jumps.
That was my experience with my dad and my dad's friends. It's like we all just go.
It's just nuts. Hi! Alright. Made it so you can't get into the desk. You don't feel trapped. Cheat sheet. Have you started one yet?
I just I just try to solve everything.
Right.
But I didn't make any cheat sheets.
Okay.
Like last time I write all homework questions, then I confused.
Yeah, writing down all your homework questions is
Yeah, then I confused. I was looking